We'll continue our series, Our Place in the Universe, with a look at our solar system. And here are some important ideas that we'll encounter. Now this is a picture of our solar system. We have the sun and we've got planets orbiting, and astronomers distinguish these 4 planets here closest to the sun. These are the inner planets, and they are rocky planets made of rock and metal. The outer planets are gaseous planets, principally made of gases like hydrogen and helium. Now you may say, well, if Jupiter is made of a lot of hydrogen and the sun is hydrogen, why isn't Jupiter emitting light like the sun? Well, the idea is there's not enough mass here, so the temperatures in the core of Jupiter are not hot enough to begin the nuclear fusion process. So while Jupiter and the sun may be made of similar materials, the sun shines and Jupiter does not. So let's take a look at some of the rotations of the planets. Here we have the 4 inner planets and the 4 outer planets, and you'll notice they have different rotational speeds. And Earth rotates at an angle like Mars does, but Venus not so much, and Mercury not so much. Uranus has an interesting rotation, seems to be sort of rotating horizontally. In this animation, we'll take a look at the relative sizes of the planets. Here we start with the 4 rocky planets compared to the size of Jupiter. A rough approximation is that about 10 Earths could fit side by side across the diameter of Jupiter. And now we see all the planets relative to the size of the sun. Again, another approximation, 10 Jupiters could sit side by side across the diameter of the sun. So we see clearly the sun is by far the largest object in the solar system. It has most of the mass of the solar system. In addition, we learned earlier that when stars are doing nuclear fusion and when they explode in supernova, heavy elements are ejected back out into space. And we said that a lot of material, a lot of heavy elements are made in these explosions. And you can see then these little rocky planets are tiny structures relative to the size of a star. So it begins to be conceivable that stars can produce enough of these heavy elements to assemble into what we think of as a big rock, the Earth, but it's tiny relative to the size of these stars. Of course, while these planets in our solar system have different sizes and their compositions are different, their spins are different, etc., what really stands out is that life has emerged on one of these planets. It's an open question whether life emerged anywhere else in our solar system. Scientists are interested in Mars because there was liquid water in the past, and so they'll be sending future missions to see if they can find signs of previous life. Some of the moons of the outer planets are interesting. Jupiter has moons. Saturn has lots of moons that are interesting places to explore to see if life could possibly take hold in such environments. So at this point then, let's take a look at what is known about how solar systems form. First, let's discuss again the principal components of a solar system. We have a star. So stars are giant clouds, giant balls of hydrogen and helium gas. So there's going to have to be some hydrogen and helium gas present somewhere for a star to form. In addition, planets are made of heavy elements, so there must be heavy elements in the beginning materials of a solar system. And where do these heavy elements come from? They came from stars, in the cores of stars during nuclear fusion, and in the explosions of stars. So at this point then, if we had a cloud of hydrogen and helium gas mixed with heavy elements, we would have sufficient materials to make a solar system. And so in this diagram, we see the sort of sequence of events that will form a solar system like the one we live in. Up top left, we start with a cloud of gas and dust. The gas would be hydrogen and helium, and the dust would be the heavy elements, little particles of materials that are composed of the heavier elements like silicon and oxygen, etc., as well as molecules, small molecules like water. So the overall idea is that the plentiful hydrogen and the lesser quantities of helium will be the nuclear fuel for the new star, and then the remaining dust will be spinning, orbiting around the protostar, and eventually will aggregate into planets. So let's take it one step at a time. As the hydrogen cloud condenses, temperatures and pressures get high enough to begin nuclear fusion. And we saw that process was a hydrogen nuclei. The nucleus of a hydrogen atom is just a proton. 4 of those hydrogen nuclei can be slammed together to form one helium nucleus, and that process releases energy. Tremendous quantities of energy are released, and that's nuclear fusion. This is why stars shine. So that's happening at the center of the cloud. Meanwhile, the dust particles are going to start to assemble into larger particles. And initially, the dust particles are so small that gravity is not driving the assembly. It's rather charges. So these particles can have opposite electrical charges. Some can be positive, some negative, and they'll stick to each other, and then they'll get larger and larger. And then when they get to a certain size, then gravity can start to take over and speed up the process of assembling larger and larger particles into small rocks, then larger rocks, and then planetary bodies. And as the planetary bodies get big enough for gravity to shape them into a sphere, it also then makes it easier to clear their orbits of remaining rocks and particles. Now, this is a nice story, but is there any evidence for this kind of thing? And for that, we'll turn to one of the most recent and most complicated telescopes ever constructed. It sits in the high desert in the Atacama region of Chile. It's called the Atacama Large Millimeter Submillimeter Array, or ALMA. And it's a set of these dishes. These are radio telescopes, so they detect radio waves from space. Now, you're probably familiar with a telescope like the Hubble Space Telescope. It is in orbit around Earth, but the Hubble telescope can collect light, visible light. And the reason they put it up in space is because the Earth's atmosphere blocks some of the light coming from space objects. So you put it up in the atmosphere, and you can collect more light. The ALMA telescopes are not detecting light, they're detecting radio waves. Now, what's the relation between the two? Well, both light and radio waves are a form of electromagnetic radiation. And we'll learn later in the course that we can think of light as a wave. And a wave has a wavelength. So here we see the wavelength is the distance from one crest of the wave to the next. So like waves in the ocean, light behaves like a wave. It's an electromagnetic wave. Again, we'll figure out what that means a little later. But there are different wavelengths of light. We're most familiar with visible light. Visible light has wavelengths from 400 nanometers to over 700 nanometers. And our eyes can detect these wavelengths of light, and we see the different wavelengths as different colors. But visible light is just a small part of the spectrum, the electromagnetic spectrum. So if here we have visible light, electromagnetic waves that have a shorter wavelength we call ultraviolet light. Even shorter wavelengths are X-rays, and even shorter wavelengths are gamma rays. If we go to the red end of the spectrum here, even longer wavelengths than red are called infrared. We experience that as heat. And even longer wavelengths are microwaves. They don't have it here. And the even longer wavelengths are radio waves. So again, there are wavelengths of electromagnetic radiation that are shorter than the purples and longer than the reds. It's just that we can't see them, and we need technological instruments to detect them. So telescopes, like the Hubble Space Telescope, they can capture visible light. And you've probably seen many images taken by the Hubble Space Telescope. The ALMA telescopes are detecting electromagnetic radiation of these wavelengths down here, in the microwave and the radio wave part of the spectrum. So what researchers did was they pointed all of these radio dishes towards a region of space, towards a star called HL Tauri. And this is what they found. Here's on the left is the larger cloud of gas and dust. And right there is HL Tauri. That's a new star. And when you magnify that image, this is what they saw. A star at the center of a disk of material. And in fact, over here on the right, we can see labeled here, we have rings in the disk and then gaps in the disk. And that's very significant. On the left here, the idea is that these gaps may be regions where a protoplanet, some small planet, is beginning to clear its orbit. So what researchers think they found here was the early stages in the formation of a solar system. A new star has begun to shine, so hydrogen and helium has condensed to the point where nuclear fusion begins, and the remaining dust has aggregated into planetary bodies that are beginning to clear their orbits. And just a comparison on the right here, the size of our solar system compared to the HL Tauri system, this is a larger system than our own. So on the left we have an artist's rendering of an early solar system with a new star, and we've got lots of dust remaining and small particles and rocks. We've got planetary bodies, and it might have been violent still as these bodies are clearing their orbits and things are colliding and such. And here we have a scene detected by some of the most complex machinery built by humans to investigate the universe. And it's just what scientists thought was going on at the origin of solar systems. Now, how big are these solar systems really? Well, here's one way to look at it back to our solar system. This picture here on the right shows us what the sun would look like in the sky if we were situated on the different planets in our solar system. So let's start with Earth. When we look up in the daytime sky, we see that the sun has roughly this size. It has that sort of degree of coverage in our sky. If we were on Venus, closer to the sun would appear larger in the sky, and Mercury even larger. If we move farther from the Earth out to Mars, then the sun gets correspondingly smaller in the sky. And with Jupiter, even smaller, Saturn, Uranus, and Neptune. You'll notice out here in the four outer planets, we don't have a sort of a daytime scene. And neither do we on Mercury. On Mercury, there is no atmosphere to scatter the sunlight. And so we'll learn that the sky appears blue on Earth because some of the sunlight is scattered into our eye and we see the daytime sky as blue. But on Mercury, there's no atmosphere to do that scattering, so the daytime sky is going to be dark. It's going to be black. And likewise out here for the outer planets. Now, of course, there's lots of gas, there's lots of atmosphere here, but it's not like you can stand on the surface of these planets, so they're not showing sort of what it would look like during the daytime. Another way to get a sense of how large the solar system is to see how long it would take the fastest thing that we know of, light, to traverse the distances in the solar system. So the speed of light is very fast. The fastest thing we know of in the universe, 186,000 miles per second, or around 300,000 kilometers per second. And the distance that light travels in a year is called a light year, and that's about 6 trillion miles. So light is a super fast thing, and now we'll use a couple more animations to show us just how long would it take light to move across distances in our solar system. The first animation will show us the speed of light around our planet. 7.5 orbits per second at the surface of Earth. So that's how fast light travels. But now we're going to use a different measure. Here we see light traveling from the Earth to the Moon. Surface to surface, 1.255 seconds. And the average distance from the Earth to the Moon is around 384,000 kilometers, or about 240,000 miles. And now let's expand the scale. Earth, Moon, and here's Mars. And here's light on its journey from Earth to Mars. And that'll take one way 3 minutes and 2 seconds. So again, light is the fastest thing in the universe, and it's taking a while to get out to Mars. And we perceive it as taking a while because these distances are so vast. Let's take a look at one more. Here we have the Sun, Mercury, Venus, and Earth, and here's light on its journey. Let's play it. That's how fast it's going. Of course, it's traveling at the same speed, 186,000 miles per second, but it appears to be slow because these distances are huge. It's going to take 8 minutes and 17 seconds for light to go from the Sun to the Earth. So when we see the light from the Sun, we are seeing the Sun as the Sun was 8 minutes and 17 seconds in the past. So these are just the 3 inner planets here. So you can see it takes a long time for light to go from the Sun to the Earth. 8 minutes. And here's one more. We'll take a look at the Sun emitting light, and here's the entire solar system, and here is light. It will take 5 hours and 28 minutes to get to Pluto. Let's help it along a little bit. We'll click here and there. It's now just made it out of the inner solar system past the asteroid belt, and it's heading towards Jupiter, passing Jupiter on its way to Saturn, and let's go past Saturn on its way to Uranus, and then Neptune, and past Neptune to Pluto. 5 hours 28 minutes. So to summarize then, the solar system is very large, and this kind of picture is not to scale. We don't get a sense of how big, how vast the distances really are.